Hello everyone, today I'll be presenting SceneWeaver, published at NeurIPS 2025. This is a joint work from Big AI and Tsinghua University. In one sentence, SceneWeaver is an agentic framework that unifies diverse 3D scene synthesis methods through a standardized tool interface and iteratively improves scenes using a self-reflective planner. There are three major approaches to 3D indoor scene synthesis, and each has clear limitations. First, rule-based methods like Proctor and Infinition Indoors. They guarantee physical plausibility through handcrafted constraints but lack scalability. Every time you want a new scene type, you need to manually define new rules, so the coverage is very limited. Second, data-driven methods like diffuse scenes and Pizzen. These learn realistic layouts from datasets such as 3D-Front. The quality is good within the training distribution, but they are restricted to a few room types like bedrooms and living rooms. Generalizing to novel scene types is difficult because the training data simply does not cover them. Third, LLM and LVLM-based methods like LayoutGPT and Artisan. Their biggest strength is open vocabulary understanding, meaning they can handle any room type described in natural language. However, their spatial reasoning is weak, which leads to physically implausible arrangements. Objects may overlap, face wrong direction, or end up outside of the room. The core problem at the bottom of the slide captures the motivation of this paper. No single approach can satisfy realism, physical plausibility, and controllability at the same time. This motivates the need for an extensible framework that integrates the strengths of each method. On the left side, you can see how previous LM-based pipelines work. The input goes through LM module A, then module B, then module C in a fixed order, producing the output. There are four problems with this design. The prompts are fixed, the module execution order also fixed. There is no feedback on generation results, so it is an open-loop system. And the tool set is also limited. In short, this is a static pipeline. On the right side is a SceneWeaver. The key difference is visible in the diagram. The LM planner reads tool cards and dynamically selects among tool A, B, and C, and whatever anymore based on the current situation. After execution, the result feeds back into the planner for the next iteration. This is a closed-loop system. Four features make SceneWeaver a self-refining and extensible agent. The reason, act, reflect paradigm, the self-reflective planner with feedback-based adaptation, the standardized tool interface for easy extensibility, and the physics-aware executor that guarantees physical plausibility. The three contributions are listed at the bottom. First, this is the first reflective agentic framework for 3D scene synthesis. Second, it introduces the reason, act, reflect design together with a standardized extensible tool interface. Third, it achieves state-of-the-art in open vocabulary scene synthesis across visual realism, physical plausibility, and instruction following. Let me walk through the framework starting from the problem formulation at the top. Given a user text query Q and a toolset D, SceneWeaver produces a 3D scene through T iterative refinement steps. At each step T, the planner P takes the previous scene, the toolset, and the query, then passes the results through the optimizer E to produce the updated scene. Now, the two core components below. On the left is the standardized tool interface. Various scene synthesis methods are abstracted into modular tools. Each tool has a tool card containing its description, use cases, strengths, and weaknesses. This allows the planner to decide when and how to use each tool. When you want to add a new tool, you just write a tool card. No changes to the framework code are needed. On the right side is self-reflective planner. You can see the cyclic structure: reflect, then feedback, then think, then action, and back again. The planner receives feedback about the current scene quality, analyzes what the most critical problem is, selects the best tool to fix it, and executes. The executor then performs physical optimization, resolving collisions, out-of-bound violations, and enforcing spatial relations between objects. Tools are categorized into three types based on their generation generality. Scene Initializer generates the overall scene layout and serves as the starting point. As shown in the images, there are three subtypes. Data-driven tools produce high-quality layouts learned from professional datasets. Real-to-sim tools offer unparalleled realism because they are based on actual 3D scans of the real rooms. LM-based tools provide superior flexibility for generating diverse and custom layouts for any room type. Microscene implementers add detailed small objects to the scene. For example, placing a keyboard and monitor on a desk or tableware on a dining table. LM-based implementers offer semantic diversity for choosing which object to place. 2D guided implementers achieve visual realism through pixel-level scene alignment. Importantly, these tools work on local context rather than the global layout. Detail Refiner corrects errors introduced by the previous tools. Rule-based refiners enforce strict spatial and relational constraints, such as making sure a chair faces the desk. VLM-based refiners fix physical properties like rotation and scale. LM-based refiners filter out irrelevant or inappropriate objects, such as removing a bathroom sink that was mistakenly placed in a restaurant. This slide shows the core mechanism of SceneWeaver through a concrete example. On the left are the tool cards. You can see initializer cards at the top, implementer cards in the middle, and refiner cards at the bottom. Each card has a description, strengths, and weaknesses that the planner reads before making a decision. On the right side is the actual planning process. The user demand is design me a laundry room. Looking at the memory of step T-1, in the previous step, the agent used the VLM update rotation refiner to correct the orientation of a washing machine, and it succeeded. The reflection score shows realism 8 point, functional 7 point, layout 8 point, but completion is only 5 point, which is the lowest. The feedback says the lack of decor or daily supplies makes the room feel unfinished. Now look at the plan for step T. The agent follows 4 steps. First, it checks whether the previous problem was solved. Yes, the rotation issue is fixed. Second, it identifies the most serious current problem. Completion is the lowest score, so it needs to add laundry objects to the shelf. Third, it lists candidate tools with confidence scores and select implementer, which is LM, to add objects. Fourth, it explains the expected outcome. Objects should be added into the shelf, and if successful, proceed to final adjustments, otherwise try a different tool. On the far right, you can see the scene evolving from step T-2 to T-1 to step T, getting progressively more detailed. This is the self-adaptive refinement mechanism. Find the lowest score, pick the best tool to fix it, execute, reflect, and repeat it. Now let us look at the quantitative evaluation. The left table shows results from closed vocabulary settings, specifically bedroom and living room. The right side shows the average score across 8 open vocabulary room types. Let me quickly explain the metrics. Number of objects measures scene richness. OB is the number of objects placed outside the room boundary. CN is the number of colliding object pairs. Then realism, functionality, layout, and completion are visual and semantic quality scores rated by GPT-4. There are 4 key takeaways from the analysis. First, SceneWeaver achieves state-of-the-art in all visual and semantic metrics while maintaining zero physical errors, zero collisions, and zero auto-violations. Second, holodeck has a high object count of 32.2 in the bedroom, but its collisions count is 38.5. This is because objects are placed somewhat randomly without proper physical checking. Third, data-driven methods like ATIS and PhysiCine generate fewer objects because they are training datasets, mainly containing large furniture items. Fourth, the completion score gap is especially large. SceneWeaver scores 9.4 in the bedroom, while other methods stays in the 4 to 6 range. This demonstrates the effectiveness of the iterative implementer that keeps adding relevant small objects until the scene feels complete. Now let us look at the visual comparisons. The top half shows results on the 3D front dataset of 4 bedroom and living room, compared against ATIS, diffusion, and PhysiCine. You can see that SceneWeaver generates scenes that go beyond data limits, with richer and more diverse object placement. The other methods produce sparse scenes with most largely furniture, while SceneWeavers fill in small objects and decorations. However, these baseline methods lack an iterative loop, so they cannot maintain context consistency across generation steps. The bottom half shows open vocabulary results for restaurant, meeting room, and kitchen compared against Layout GPT, Holodeck, and iDesign. SceneWeaver demonstrates the highest coherence with user queries, looking at the restaurant row for example. Holodeck places many tables but the arrangement looks chaotic, while iDesign is clean but sparse. SceneWeaver has well-organized table arrangements with tableware and utensils placed on each table. This is achieved through strict physical constraints combined with the reflective loop that iteratively maximizes visual quality. Let me wrap up with 4 key takeaways. First, SceneWeaver is the first reflective agent framework for 3D scene synthesis, using the reason, act, reflect paradigm for iterative scene refinement. Second, it unifies various scene synthesis methods through a standardized and extensible tool interface. Adding new tools only requires writing a tool card. Third, the physics-aware executor guarantees physical plausibility, achieving zero collisions and zero out-of-bind violations. It is built on Infinition and Blender and supports export to Isaac Sim for embodied AI applications. Fourth, SceneWeaver achieves state-of-the-art in both common and open vocabulary settings. In human studies, it was preferred over 85% of the time, with over 90% superiority in diversity. The core message of the paper is no single approach is sufficient. SceneWeaver unifies all their strengths through an extensible, self-refining agent. Thank you.